A thermometer measures the average mechanical motion of molecules. The red liquid rising in the glass responds to a microscopic bombardment, where billions of invisible particles strike the bulb every second. This is the core of kinetic theory. A gas is a collection of tiny particles, atoms or molecules, in constant, incessant random motion. In an ideal gas, the interactions between these molecules are negligible. They move in straight lines, following Newton's first law, until they collide with each other or the walls of their container. Ludwig Boltzmann was the architect of this statistical view. He recognized that while individual atomic behavior is chaotic, averages explain the predictable rules of thermodynamics. He identified a state called thermal equilibrium. Despite the violent collisions occurring at the molecular level, the system's average kinetic energy remains constant. This equation bridges the micro and macro worlds. It establishes that internal energy, E, is directly proportional to absolute temperature, T. The two are connected by the Boltzmann constant. For an ideal gas, the internal energy depends on temperature and nothing else. This mechanical motion acts as a strict ledger for every joule of energy in the system. If heat is a measure of motion, the geometric shape of a molecule dictates how much energy it can store. Physicists quantify this through degrees of freedom. A degree of freedom is the number of independent coordinates required to specify a molecule's exact location and motion in space. Motion is divided into three distinct modes: translation through space, rotation around an axis, and vibration along a bond. A degree of freedom must contribute a squared variable to the total energy, like velocity squared across the x, y, or z axis. The law of equipartition of energy states that in thermal equilibrium, total energy distributes equally among all active degrees of freedom. Every valid quadratic mode of motion claims exactly 1/2 kBt of thermal energy. The law of equipartition acts as a thermal accountant. A molecule's geometric complexity determines exactly how many slots it has to hold these energy tokens. We begin with a monatomic ideal gas, like argon. A monatomic molecule is effectively a zero-dimensional point mass. This atom moves linearly through three-dimensional space, giving it exactly 3 translational degrees of freedom. The kinetic energy requires one velocity component for the x, y, and z axes. Since each is a squared variable, equipartition assigns one energy token to each. Summing these reveals the monatomic internal energy, 3/2 kBt. We ignore rotation for a single atom. Its radius is so small that its moment of inertia is negligible, making rotational energy physically irrelevant. The simplest gases in the universe are capped at 3 degrees of freedom, storing energy solely by moving linearly through space. Geometric complexity increases with diatomic gases, such as oxygen or nitrogen. These molecules function as rigid rotators, a one-dimensional line connecting 2 point masses. This structure maintains 3 translational degrees of freedom as it moves through space. Because the molecule has physical length, it can tumble end over end. There are 2 independent axes of rotation perpendicular to the bond joining the 2 atoms. Rotation along the interatomic axis itself is discounted. The mass is concentrated so closely to the center that the moment of inertia is effectively zero. We add these 2 rotational modes to the thermal ledger, including moment of inertia and angular velocity for both axes. Because angular velocity is squared, each axis gains another 1/2 kBt, increasing total capacity to 5/2 kBt. By creating a 1D structure, a gas gains these additional rotational modes. It holds significantly more heat than a monatomic gas at the exact same temperature. At higher temperatures, molecular bonds are not perfectly stiff. Molecules like carbon monoxide demonstrate that the rigid rotator model has limits. The bond acts as a microscopic spring. It can stretch and compress, which introduces a mode of vibration. Vibration is mechanically different from rotation. It functions as a one-dimensional harmonic oscillator. This oscillator requires energy for the kinetic motion of the atoms and potential energy to stretch the bond against interatomic forces. The ledger must record 2 distinct quadratic terms for vibration, one for the kinetic velocity and one for the structural potential. The equipartition law assigns a 1/2 kBt to every quadratic term. Consequently, this single vibrational mode receives 2 full tokens. The total energy for a vibrating diatomic molecule includes 3 translational halves, 2 rotational halves, and 2 vibrational halves, totaling 7/2 kBt. Vibrational modes require the system to balance kinetic motion against structural tension, making them highly efficient energy sinks. This microscopic accounting explains how real-world gases respond to heat. We measure this through specific heat capacity, the energy required to raise the temperature of a bulk gas. Consider two tanks, monatomic argon on the left and diatomic carbon monoxide on the right. We inject the exact same amount of thermal energy into both. Argon's temperature spikes, while carbon monoxide rises slowly. Argon has 3 degrees of freedom. Added heat immediately increases the atom's translational speed. Carbon monoxide has 7 degrees of freedom. Energy diverts into rotation and vibration, leaving less to increase linear speed. A thermometer responds to the force of molecules physically colliding with the glass bulb. Only linear, translational motion creates the momentum transfer required to register a temperature change. Since rotational and vibrational energy do not contribute to the impact force against the bulb wall, they are thermally invisible. The macroscopic thermal behavior of our universe is hard-coded by the microscopic geometry of its molecules.